All right. I just wanted to let you know I've made small changes to next week's schedule. So I added that we're talking about 9.4 and 13.3 today. And so on Monday, not next Monday, but the next Monday that we meet, we're going to work on homework 11 in class, which is just so some of the problems that we've talked about, some of the problems that we will get to if we have time, and problem, shouldn't have zoomed in on this page. Um, problem 6 only for 13.3, which I think is fun. So we'll spend time in class doing that. And then you can go home, write up your solutions. And then I've moved the due date for homework 11 to be the Wednesday because I won't be here on the Friday. Um, and that Wednesday will serve as our official review day. And so I will do my best to write the final exam over Thanksgiving break. My plan is to come up with wacky and zany scenarios for you to solve using combinatorics, logic, and graph theory. And so on Monday, if you would like to come up with problem scenarios that could be used, then we can do that. And then next Friday, I've planned for just asynchronous review. So you'll have all the materials you need by then. If you'd like to come and talk, like come in this room, it's reserved for us, and talk with your classmates. Here's how. And so you can like do your own review that day. Yes.
When you say like we'll have everything we need to study, are you making like a study guide?
Yes.
Oh,
Yeah. My goal is to have that. I'm gonna have the final written, probably a practice written by Monday-ish. But that Monday, if you come up with really interesting things that I want to include, I will make the changes. And at the official review day, you'll have all the study guide, practice exams, and all that you'll need for the final. Other questions? Okay. Okay. So we're going to talk about spanning trees today. So we've talked about trees. One thing that I want to clear up, which I heard today, is the confusion where there's a difference maybe between wait, no, that's not the same thing. No, it is the same thing. Okay, so these graphs are isomorphic, right? Cool. So are they both trees? Yes. So they're isomorphic, meaning they have the same structure. So like this vertex corresponds to that vertex, this corresponds to that one, that corresponds to that, and then the two leaves are there as well. They're isomorphic and they're both trees. But when we call one of them a rooted tree, so like if we designate this as a root, that means this tree is now rooted. And that just involves us imposing this structure onto the tree to say when we designate this node as the root, that makes it a rooted tree. Unless specified otherwise, it's just your pun may be intended, garden variety tree, right? Rooted tree is some additional imposition that we apply to the graph. And usually we assume that a tree is undirected. And undirected means that, like on Instagram, both people follow each other, and so we just ignore the arrows. And so we assume undirected unless specified otherwise. Okay. So to recap last time, let's go back over here. So when we have a rooted tree, so this is some imposition that we have applied, we have a rooted tree, and that way we can align the tree into levels where we have a parent and then a child. Yes,
Can you tell a tree is rooted by looking at it, or does it have to be stated?
it has to be stated. Right, so here we have said that this is the root. And sometimes when you see, like if you go and look at things on the internet, it may not say like this tree is the root, but it's drawn in a way that like if I had not said that, but you can see how it's drawn, you could say, oh, this is a rooted tree because of the way that it's drawn, this is clearly the root. Okay, I'll put that back. All right, and so this is one of the things where I don't like the way the textbook did this, where they were like, we've got a tree that's directed. And that's the only way we can draw a rooted tree or draw a binary tree. That's not true. This is the way that they chose to convey this information, where we could have drawn this with bidirectional arrows. We could have drawn it undirected. This is just a choice that the book authors chose to make. But when we draw a tree in this way, or in fact any tree, we still have leaves. So like if we have a regular path, that's a leaf and that's a leaf. It's still a tree and it's still got leaves regardless. But so when we draw a tree in this way with this level structure, we've got parent and children, and then children on the same level are called siblings. And this way of drawing it is with levels. The height is the maximum level that we have in our tree. And a binary tree is this additional restriction where each parent has at most 2 children. Okay, and so where we did not get to yet is a complete binary tree, which is just a binary tree where every possible, okay, let's read the book. One for which each vertex that is not a leaf has exactly 2 offspring. So each vertex that isn't a leaf has exactly 2 offspring. So for example, this one that we drew before is a complete binary tree because the root has 2 offspring, and then the ones in the middle each have 2 children, and then these are leaves, so they're fine. Yeah.
Can you add on more things where it's like a complete directed binary tree? Like can you
Yeah.
put multiple things?
Yeah. They're just adjectives. So like tree is what it is, and complete has to say of the possibilities, we're including all of them in terms of like edges. Directed is just a quality applied to the edges. What else did I want to say about trees? There was something. I forget. We'll get there later. We use binary trees for something like there's a machine learning technique called decision tree, which is where we say, this is basically like, you know how we talk about if and else, like branching? It's a tree where we say if condition is true, take that path, If condition is false, take the others. So we can say if that, otherwise take the other path. And we can split this as many times as we need. So if we've got multiple conditions, then there's maybe more than 2 children. If it's just if and else, then it's a binary tree. So trees are super useful, graphs are super useful for generalizing even simple programmatic structures that you learn in like programming 1. This is why I love graphs. Okay. All right, let's talk about a spanning tree. So let's say we have the butterfly graph. And we want to, let's assume that this butterfly graph is, I don't know, roads between, or like, let's see, this is typically like utilities in different cities. And we want to figure out how are we going to connect all the cities by utilities, but without having, like, we want to limit redundancy, right? This is where spanning trees come in. So a spanning tree, and we say of a connected, that's not how you spell connected. Graph G is a tree, surprise, surprise, whose vertex set is V of G and whose edge set is a subset of E of G. So basically, we're gonna take all the vertices from this graph and have certain edges that connect all of this, like connect all of our vertices together. So we say it's tree, it's not a forest, so it must be connected. So we can't say like that's not a spanning tree. We have to connect all of the vertices together. That would be a spanning forest. So for example, that could be a spanning tree where we've got all of the vertices, but we only have some of the edges. So that means that we don't have the, I don't know, closing wings of the butterfly. This is also used, for example, like let's say we are an airline company and let's suppose that we could have a direct flight from every location to every other location. But let's assume that this is our graph. Oh, there's a flight Chicago to New York. So let's assume that this is our current airline offerings. We want to figure out, like, we want to save money. So we want to figure out which flights can we cut while still ensuring that if you start at any city, you can get to any other city. We're looking for a spanning tree. And so, for example, one would be to, what the book has is we cut the flight from LA to Miami, and we cut the flight from LA to New York. And then we're left, So we can still get to Miami, we just have to go through Chicago and New York to get there, which is not very efficient, but like still enables someone to fly from LA to Miami. Someone in New York can still get to Dallas if they have a connection in Chicago, right? So this is a spanning tree. There's also the notion of a minimum spanning tree. So this is where weights come in, where we add numbers to the edges to say that maybe there's like a number of miles or there's a cost associated with offering this flight from LA to Miami. And if that cost is too much, we're not going to include that edge in our minimum spanning tree. So let's talk about that in a little bit more detail. All right, so the book's got this. So now we're transitioning to 13.3, where they actually say, here's what's up about spanning trees. So we've got A, B. I don't like the way that they labeled this graph, but so it is. 7, 2, 3, 5, 4, 2, and 3. Okay, so we've got a labeled graph because the vertices have names. We've got a weighted graph because the edges have numbers. And so at a high level, so from a graph theorist perspective, this is all we get. From someone in industry, they look at this as these are cities and these are the costs associated with having some infrastructure going from A to B, right? But as graph theorists, we get to kind of stand above that and just say, that's a weighted graph. I can do graph algorithms with it. Okay, so we want to find a spanning tree for this. And furthermore, we want to find the minimum spanning tree. Minimum spanning tree, which we define as the spanning tree. So not just any spanning tree, but the one with minimum weight. Again, computer scientists are great at naming things, and so we are naming it what it is. As long as we know what a spanning tree is, and we can see that the graph has weights on it, we want to find the spanning tree with the minimum cost, minimum weight. All right, there's two general ways to do this. I skipped past my notes for that one. So in general, to find a minimum spanning tree or any spanning tree, one strategy is to remove edges. The other is to kind of build or choose the existing edges that are in our graph. So either we start with this and knock things away, or we're like, I'm going to choose that one. I'm going to choose that one. So we're going to look at two algorithms. Both of these are ones where we're choosing edges, but we choose them in slightly different ways. Okay, so first, we're going to look at an algorithm designed by a guy named Kruskal. And the first step here is to sort edge weights in, the book says, non-decreasing. So that's just ascending order. And so we're going to say that T is going to be our spanning tree, our minimum spanning tree. And we're going to start T out empty. The book adds an empty subgraph of G, which basically means we've got all our vertices. We're just choosing the edges to include. And so we've sorted the edge weights. And so what we do is we just choose the smallest one. So like we've got them sorted in ascending order. Choose the first one. So select the smallest edge weight. And now we don't want to just go on with it because it may break our rules of being a tree. Because, so we need to have a condition saying if this edge does not create a cycle in T, add it to T. Otherwise, throw it away. And so we're going to keep doing that until every vertex is connected. So we'll maybe be specific. Continue steps 3 and 4 until we've connected every vertex. What the book says is until T contains V minus 1 edges, which is basically we've reached tree stage. Great. That's how we do it. All right. I wish I could put this on. All right. Let's select this. Copy. I'm going to paste this here. Okay. So this is the graph that I'm going to run this algorithm on. Step 1 is to sort the edge weights in ascending order. So let's find the smallest. The smallest are weight 2. So BC have weight 2. EF have weight 2. Then are the 3s. DE is 3. BD is 3. DF is 4. BF is 5. AB is 7. Did I miss any? Cool. All right, great. We've sorted it. Step 1 complete. Let's go back and see what's next. Start T as the empty subgraph of G. So I'm going to say, so either like on a test, maybe you bring colored pencils and you can like draw over the tree, or you could draw it separately. So I'm going to draw it separately. A, B, C, D, E, and F. Okay, step 2 complete. Select the smallest edge weight. What's the smallest edge weight? BC of 2. So that's step 3. Step 4 is if this edge does not create a cycle in T, add it to T. That's T. Will BC not create a cycle? Yeah, because there's nothing in there. So currently our weight is 2. So we've added it. Great. Now we repeat the steps. So BC, done. The next smallest edge weight is EF. EF, will it create a cycle? Nope. Our weight is now 4. DE. DE, will it create a cycle? Nope. So we add it. 4 plus 3 is 7. BD, with weight 3, will BD create a cycle? Nope. So we add it. 7 plus 3 is 10. DF, will it create a cycle? Yep, it'll make a triangle there with D, E, and F. So we do not add it, and we proceed to the next thing. Then BF, will BF create a cycle? Yes. So we do not add it, proceed to the next thing. Will AB create a cycle? No. So we add it. And now we have 1, 2, 3, 4, 5 edges. 1, 2, 3, 4, 5, 6 vertices. So we're done. So I stopped adding things together. 5 plus 5 plus 7. Our weight is a total of 17. Questions? Cool. Let's look at another algorithm. So for Kruskal, we sorted the edge weights. For prims, we're going to not look as objectively about this, and we're gonna like put a blindfold over our eyes, pick a vertex at random, and that's gonna be our starting point. And then from there, we're gonna build up the tree starting from that vertex. So at each vertex, we're gonna ask, what's the smallest available choice I can add an edge, and then we'll add that edge, as long as it doesn't create a cycle. So we'll start off, let T be an empty subgraph of G. For step 2, we're going to choose a vertex at random. So we'll say choose any vertex. We'll call it V naught. And the book says put it in T. Even if we like pre-populate our graph, just remember which one we started with. Book next says, from among the elements of E having one endpoint in VT and one endpoint in VG minus VT, select one of smallest weight. Put this edge in its other endpoint in T. Let's think of a better way to say that. So that's like the rigorous definition, absolutely correct. Let's say of
Adjacents.
yeah, so of edges available to vertices in T that will not create a cycle in T choose the smallest. I added of edges available in G, 2 vertices in T that will not create a cycle in T. Choose the smallest weight and add it to T. Then step 4, repeat until a tree, spanning tree. Okay. Let me draw a different graph. Okay, and the weights here are, so these are J, K, L, H for some reason, I inside G with weights 1, 2, 6, 3, 7, 4, 5, and 8. All right, this is my original graph. Would someone like to choose which vertex we start with? Sure. K. All right, we're starting with K. Step 2, done. Step 3, of edges available in G to vertices in T that will not create a cycle in T, choose the smallest weight and add to T. What vertices or what edges do we have available? So we can go from K to I, we can go from K to J, we can go from K to L. So 1, 5, or 7, which one wins? 1. And so we'll choose the edge from J to K. So we add J to our tree and we add the edge weight of 1. Now we have multiple options. We could go from K to L. We could go from K to I. Now that we've got J though, we could also go to G or we could go to I with a different weight. So from the choices of K to L for 7, K to I for 5, J to I for 4, or J to G for 2, which one will we choose? J to G for 2. Because that's the smallest edge weight of our available options. Okay, I'm gonna draw lines over here. So now G is unlocked, and so of the places we could have gone from K and J, now we also have G as an option. So what's our next best available move? J to I think so, because that's weight 4, and all of the other options are, let's see, 5, 7, or 6, which are all bigger than 4. So J to I for 4. Okay. now we have an option of 5, 7, 6, or 8. So we're going to choose the option 5, right? Why not? It's a cycle. So now that we've chosen I, this one is like automatically disallowed. Okay, so which one do we actually end up choosing? G to H for 6. I feel like we're playing Jeopardy again.
What is H?
What is H? For 6. All right. What's next? So let's see. G to H for 6. What's next? H, what is L from H for 3? Are we done? Yep. So we've gotten all of our vertices. Anything else that we add would create a cycle. So we're done. And this weight is, that's 5 plus 6, which is 16, which is our minimum spanning tree. Okay. So I would like you, let's see, what do I want to do? I want to do that one. So we've got a little bit of time left. Let's draw, I'm going to draw this graph, and then in your neighbor groups as before, figure out what the minimum spanning tree is. Okay. J, actually, nope, this is just going to waste time. It's here. Nope, no, thank you, Fourscore. This is all the way in 11, 13 point. Spanning tree, spanning tree. There we go.
Nice and easy.
Graphs are, so like this looks complicated. Graphs in real life are way more complicated. And so the goal is to like learn general algorithms so that when we get and practice on simple graphs, no pun intended, less complex graphs, where once you get like some super weird complex graphs, you can just apply the algorithm and be on your way. Okay. All right. Neighbor groups, go. Question. All right. Thank you. Have a happy Thanksgiving. See you not next week.